In the previous few lectures, we looked at virtual networks. There's actually far more to virtual networks, but it's difficult to explain without having specific solutions in mind. Therefore, in the next set of lectures, we'll examine other infrastructure components, and then once we've built some, we'll loop back around and examine some more advanced topics. So first, let's look at virtual machines. Virtual machines are still used by many companies moving to the cloud. In fact, it's often the first step when companies want to begin their cloud adoption journey, i.e. by taking a lift and shift approach. In addition, many legacy applications cannot simply be refactored to leverage more modern PaaS solutions, such as SQL, Azure or web apps. Therefore, virtual machines provide the simplest and quickest way to start using Azure. They also provide many other benefits. For example, by building them atop virtual networks, it's far easier to integrate them with on-premise solutions in hybrid scenarios. Now, all this doesn't mean they have no additional benefits. VMs in Azure allow for easy management and monitoring, provide a whole range of available operating systems and versions of those operating systems. They can be built as scale sets or in availability sets to provide better resilience. The fact that configuring IaaS components, which includes VMs, accounts for nearly half the AZ-300 exam demonstrates just how important this topic still is. So virtual machines are actually built of a number of separate components, and this is important to understand as what makes VM so flexible. It's also important to understand that when you want to remove a virtual machine, it's not just a case of removing the virtual machine. You also need to delete all its components individually. So a virtual machine consists of the virtual machine itself. It will generally have one or more disks, so the first disk would have the operating system, and then you might have data disks attached. And you might have one or more virtual network interface cards. Each interface is connected to a VNet, and therefore it gets an internal IP address on that VNet. You can also add a public IP, which provides external connectivity outside of that VNet. The public IP is optional, and for security purposes you wouldn't use them in a hybrid scenario when you want to limit connectivity to an internal, i.e. an on-premise, network via a VPN. Finally, VMs also get a network security group by default. Now, network security groups are very important. They allow you to define specific network security rules, i.e. firewall rules, to allow specific inbound and outbound traffic to specific sources and destinations on set ports. So, for example, you might want to limit certain inbound traffic to a specific network, such as your internal corporate network, i.e. so that you can RDP in or remote control your virtual machine from an internal network, but not from the public internet. But on that same virtual machine, you might want to allow HTTP traffic out to the internet so that that virtual machine can actually browse the web, for example. Let's look at disks in a little bit more detail. So when you create a virtual machine, you create one or more disks, and disks can be managed disks. So managed disks handles the Azure storage account creation and management in the background for you, so you never actually see that underlying storage account. But this ensures you don't have to worry about the scalability limits of that storage account. When you create a virtual machine, you specify the disk size and the performance tier, standard or premium, and Azure creates and manages that disk for you. As you add disks or scale the VM up and down, you don't have to worry about which storage is being used. The available types of disks are ultra disks, premium solid state disks or SSD, standard SSD, and standard hard drives or HDD. This table provides a comparison of the different type of disks you can have. But in brief, ultra disks tend to be for the biggest and the fastest workloads that you can have. Premium disks are again for very fast applications and provide disks up to 32 gigabytes. And then we start going down through the tier, and as you can see, you start getting slower performance and slower throughput. Of course, as you start at the standard HDD, they are obviously far cheaper than an ultra disk. So when you're designing your virtual machines, you have to take into account and balance the performance requirements with the cost. So all managed disks are highly durable and available. This means they are designed for 99.999, that's 5 nines, % availability. Managed disks achieve this by providing you with 3 replicas of your data, allowing for that high durability. If 1 or even 2 of the replicas experience issues, the remaining replicas help to ensure the persistence of your data and provide high tolerance against failures. Managed disks, you can create up to 50,000 disks of a type in a subscription per region. This allows you to create thousands of VMs in a single subscription. They're also integrated with availability sets, which we'll look at shortly. Managed disks are integrated with availability sets to ensure that the disks of the VM in an availability set are sufficiently isolated from each other to avoid a single point of failure. They're also integrated with availability zones, and again we'll look at availability zones shortly. Finally, to protect against regional disasters, Azure Backup can be used to create a backup job with time-based backups and backup retention policies, and you can implement RBAC or Azure Role-Based Access Control to assign specific permissions for a managed disk to one or more users. Before we move off disks, it's important to talk about encryption. Managed disks offer 2 kinds of encryption. The first is server-side encryption, which is performed by that storage service, and the second is Azure Disk Encryption, which you can enable on the OS and the disks for your VMs. So, server-side encryption provides encryption at rest and safeguards your data to meet organizational security and compliance commitments. Server-side encryption is enabled by default on all managed disks. You can either allow Azure to manage the keys for you, or you can actually provide the keys yourself. Azure Disk Encryption allows you to encrypt the OS and the data used by a virtual machine. This encryption includes managed disks. For Windows, the drives are encrypted using BitLocker. For Linux, the disks are encrypted using dmcrypt. The encryption process is integrated with the Azure Key Vault to allow you to control and manage those encryption keys. And again, we will cover those in more detail later on. So we mentioned earlier about availability sets and scale sets. So let's talk about those. So first we have the concept of something called fault domains. Fault domains are used to control where VMs are built. A fault domain is essentially a set of servers that share the same power and network switches within the data center. Therefore, if 2 virtual machines run the same fault domain, any issue occurring at that switch or power source could affect both your virtual machines. Update domains are used to control when the underlying hardware that Microsoft manage are patched and rebooted. As Microsoft performs maintenance on the underlying for you, there are times when that hardware might need to be rebooted, and sometimes the updates might require the virtual machine itself to be rebooted. An update domain defines when these events occur, so all servers in the same update domain would get rebooted or affected at the same time. So to get around this issue, we have availability sets. By default, Microsoft automatically manages the placement of your virtual machines. Therefore, 2 virtual machines could be running in the same fault and update domains. By creating an availability set and by assigning virtual machines to that availability set, you're informing Microsoft to distribute those VMs across fault and update domains. Therefore, in the event of a downtime from either failure by maintenance, it would affect only those VMs in that domain. And because the others are distributed, they would not be affected. Using this, you can build applications that span multiple virtual machines and then put them in an AV set. Therefore, your application would not be affected if one of those update or fault domains went down, as the other 2 virtual machines would carry on running, providing services. Next we have scale sets. So a Azure virtual machines let you create and manage groups of identical load balanced VMs. The number of VM instances can automatically increase or decrease in response to the demand on a defined schedule. Scale sets provide high availability to your applications and allow you to centrally manage, configure and update a large number of VMs at a time. So scale sets are built from virtual machines. So with scale sets, the management and automation layers are provided to run and scale your applications. Of course, we could just build our own VMs manually ourselves, as we saw in the previous example with availability sets. However, using virtual machine scale sets has a number of advantages, as we can see in the following table. The main benefits with scale sets is that they are automatically created from a central configuration, i.e. you build one virtual machine and the Azure platform will automatically replicate that virtual machine into those scale sets. You can automatically create and integrate them with an Azure load balancer or an application gateway, and they are automatically distributed across availability zones. Finally, with virtual machine scale sets, you can set auto scale, which means you define a minimum number and a maximum number of VMs in that scale set and set certain limits when it needs to spin up or spin down those virtual machines, or you could do it on a schedule. So for example, you could set additional virtual machines to be spun up within the scale set if the CPU threshold for them reaches 80%, or you could set it to automatically spin up additional virtual machines at certain times of the day or the month, for example month end. When building virtual machines within Azure, there are actually lots of different types you can use to build. Rather than know each individual size, type and cost, for the exam you do need to remember all the different types that you can use, known as the series of VMs. The first few series of VMs are fairly straightforward. The series A's are basically just balanced entry-level servers. So these will generally be used for dev, test and proof of concepts. They're scenarios where you might have low traffic, so small to medium servers. Next we have the BS series. These are quite a special kind of VM. They're low cost, but they're what's known as burstable, which means as they need more power, they can automatically have more power assigned to them for that particular moment in time. Again, the use cases tend to be fairly small, dev, test and proof concepts, but they're also quite well suited to microservices. Next we have D series, or the general purpose servers. These are an optimal CPU to memory ratio and are most suited for most normal use cases. The DS and DAS series also support premium SSDs, whereas the standard D series only supports standard SSDs. Again, these would generally be used for enterprise applications, smaller relational databases, caching and analytics. As we move up the series, we start to get more specialised use cases. So the next one is the DC series. These have special CPU processing protection using something called secure enclaves. And they're ideal for customers who are quite worried about the sharing of data or leaking of data in shared environments. So for example, they support confidential querying of databases, consortium networks, and secure multi-party machine learning. E-series machines are the first where we start to optimize either memory, compute or storage. So E-series are in-memory optimized. This means there's a high memory to vCPU core ratio, which makes them well suited to applications that require lots of in-memory processing, such as certain type of databases, particularly SAP HANA, SQL Hekaton and other large memory in-memory workloads. Almost the opposite to the E-series is the F-series, which is compute optimized. These have a higher CPU to memory ratio and are designed for compute intensive operations that need to be able to store lots in memory while doing that. So think batch processing, web servers, analytics and gaming. G series is a bit of a combination. It's a memory and storage optimized. So these are enhanced general purpose, so like the D series ones, but they've got twice as much memory and up to 4 times more local SSDs that they can use. Again, good use cases for these tend to be large SQL and NoSQL databases, ERPs, SAP and so on. So think standard D series, but with more power. Again, in line with that, we then get the high performance compute. So these are good for specialist high performance that require specifically high bandwidth. So these tend to be quite specialist use cases, particularly in the mathematical and scientific world, where you might want to have use cases such as fluid dynamics, finite element analysis and seismic processing. Next we get storage optimized. So this isn't just necessarily about having large disks, but it's about having high throughput and low latency to those disks. Again, this tends to be well suited for particular types of databases, namely NoSQL databases such as Cassandra, MongoDB and Redis. The final 2 series are again becoming more and more specialized. So the M and MV2 series are like the E series in that they are memory optimized. However, they support far more vCPUs. So for example, the M series, you can have up to 128 vCPUs on a single server, whereas the MV2 supports up to 416 vCPUs on a single server. And finally we have the N series. So these servers are GPU enabled using the NVIDIA chipsets, and they're ideal for intensive graphic workloads or other workloads that use that type of computational processing such as machine learning. So again, the typical workloads might include simulations, deep learning, graphics processing, video editing, even gaming and remote visualization. So for the exam, you need to understand the different use cases for the different series. That's enough theory for now. In the next lecture, we'll get on and start building some virtual machines.